So we are going to talk about limits. You might have seen the epsilon-delta definition of a limit, which says that the limit as x approaches c of f of x equals L, if and only if, for every number epsilon greater than 0, there exists another number delta greater than 0, such that if the distance from x to c is less than delta, then the distance from f of x to L is less than epsilon. I have a video explaining the epsilon-delta definition, so you can check that out in the description. Now, the epsilon-delta definition of limits is a very important part of proofs in calculus. And you might have seen a few examples of people using the epsilon-delta definition to prove that a limit equals some number. But those proofs can be kind of confusing because it seems like we could make the limit equal anything we want. I mean, no matter what epsilon we choose, can't we just choose some value of delta that's really small to make the limit expression work? But if we could make the limit equal two different numbers, or any number that we want, then the idea of a limit is going to be pretty useless. So in this video, I want to do something a little different. First, we're going to go through two examples of proving that a limit doesn't equal some number. And at the very end, we're going to prove, using the epsilon-delta definition, that every limit has at most one value. We can never have a limit that equals two different things at the same time. So our goal is to prove that a limit does not equal a certain value of L, which means we have to disprove this epsilon-delta definition over here for that specific value of L. Before we do that, I want to look at disproving a different statement. Let's say we have a room full of people who are wearing different colored shirts. And I tell you that everyone in the room is wearing a red shirt. Well, if we look at the room here, that's obviously wrong, right? Why is it wrong? Well, because look, right here, there's someone wearing a blue shirt, and that's not red. So we've disproved the statement that everyone in the room is wearing a red shirt, because there's an example right here of someone who is not wearing a red shirt. Let's think about how that reasoning works more generally. When I say that everyone in the room is wearing a red shirt, I'm making a claim that applies to all people in the room. And in order to disprove that a statement is true for all people in the room, we only have to find one example of when it's not true. We only have to find one person who doesn't satisfy the condition that they're wearing a red shirt. If we look at the epsilon-delta definition of a limit up here, it's also a statement that we want to prove for all epsilon greater than 0. And in order to disprove that the statement is true for all epsilon greater than 0, all we have to do is find one example, one value of epsilon, such that the rest of the statement is not true. And if we do that, we've disproved the entire statement. So in order to disprove the statement that the limit of some function equals L, all we have to do is prove that this statement right here is false for one value of epsilon. And after that, it doesn't matter what's happening for the other values of epsilon, because we know that the statement is not true for all epsilon, which means that L cannot be the value of the limit. So now let's start our first example. We're going to define a function f by f of x equals 6. So this is a constant function where no matter what number we put in, it's always going to give us the answer of 6. And our goal is to prove that the limit as x approaches 3 of f of x does not equal 6.5. So let's look at a little graph of this situation. If we look at the input x along the horizontal axis and the output on the vertical axis, our function is just going to take the value of 6 everywhere. So it's going to be this flat line. That is our f of x. And if we look at the limit value, at the value of x equals 3, we want to disprove that the limit equals 6.5, which is going to be somewhere up here. Now, when we look at the epsilon-delta definition, really the key part of this definition is the last statement right here. The distance from f of x to the limit value L is less than epsilon. So before we do anything else, let's take a look at what this expression, f of x minus L, looks like in our specific case. So the absolute value of f of x minus L. Well, the value of f of x is always 6. That's how we define the function. So this f of x part becomes 6. And the value of L that we're looking at is 6.5. So this L right here becomes a 6.5. And 6 minus 6.5 is negative 0.5. We take the absolute value, that becomes positive 0.5. So when we look at the epsilon-delta definition, the statement says that the distance from f of x to L is less than epsilon if we pick some certain condition on the distance between x and c. Right now we've proved that this distance right here is always equal to 0.5. So what happens if we pick a value of epsilon that's less than 0.5? Let's say we pick epsilon equals 0.4. For this value of epsilon, can we ever have that the distance from f of x to L is less than epsilon? Well, no, because the distance from f of x to L is 0.5, and 0.5 is not less than 0.4. So this statement right here, the absolute value of f of x minus L is less than epsilon, that's going to be false no matter what the value of x is, because this is always 0.5, and we picked epsilon equal to 0.4. Now, to be a little bit more formal, we need to take a look at the rest of the definition in this box here. What we really want to disprove is that there exists some delta greater than 0, such that if the distance from x to c is less than delta, then the distance from f of x to L is less than epsilon. Now we know that this statement here, the distance from f of x to L is less than epsilon, that's always false when we have epsilon equals 0.4. So let's say, suppose delta is greater than 0. We have some arbitrary number here. Our goal is to show that this gives us a contradiction, and if there's a contradiction for every possible value of delta, then that means that there does not exist a delta greater than 0 satisfying this condition. So let's say we have our delta greater than 0. The statement says that if the distance from x to c is less than delta, then this statement right here holds. So let's first find some number, x, such that the distance from x to our limit value 3 is less than delta. So we can do that by taking x equals 3 plus delta over 2. So the reason we want an x value of 3 plus delta over 2 is that the distance from 3 plus delta over 2 to the limit value of 3 is delta over 2, and that is less than delta. So we found some value where the distance from x to c is greater than 0, because it's delta over 2, and it's also less than delta. So this first statement is true. We found a value of x that satisfies this first condition. And if that's true, then that implies the distance from f of x to L is less than epsilon. But this is false. So we found a value of x where the first statement is true, and that statement is supposed to imply the second statement, but the second statement is false. So that gives us our contradiction. So we've shown that no matter what value of delta greater than 0 we choose, we get a contradiction because this statement A implies B is always going to be false. We have something true over here and something false over here. And that means that there does not exist a delta greater than 0 satisfying this condition, which means that this statement is false for the value epsilon equals 0.4. And like we said earlier, if we disprove it for one value of epsilon, that's all we need. We don't have to look at any other value of epsilon because we know that this entire statement is going to be false, and that means that the limit as x approaches 3 of f of x does not equal 6.5. So the example where f of x is just a constant function is the simplest example when we're doing limits. So let's look at an example of a non-constant function, which is f of x equals x. And our goal will be to show that the limit as x approaches -1 of f of x does not equal 0. So let's take a look at the graph. If we have our x-axis right here and our y-axis right here, we have the function f of x equals x, that's just that line straight through, and we have the value of -1, and this is going to be the point we're interested in, but the limiting value we're looking at is the vertical value of 0. Now remember, the key to doing this proof that the limit does not equal the value of 0 is to disprove this last statement right here. The distance from f of x to L is less than epsilon. So let's look at what this expression equals. We take the absolute value of f of x minus L. First of all, f of x is equal to x. And the value of L that we're looking at is 0. So the absolute value of x minus 0, and that's just the absolute value of x. So just like before, our goal is to prove that there does not exist a delta greater than 0 satisfying this condition for some value of epsilon. So let's suppose we have some value of delta greater than 0 and see if we can find a contradiction to show that that delta does not exist. So suppose delta is greater than 0. We want to find some number x, which is a distance less than delta away from this limit input -1. Well, in order to do that, we can take the value of -1 minus delta over 2. Now the reason we look at the value -1 minus delta over 2 is that we want the distance from this to -1 to be less than delta. So if we just take -1 and we move over by a value of delta over 2, which is less than delta, we know we're going to stay inside that range. But you might be wondering, why did I look at minus delta over 2 instead of taking -1 plus delta over 2? Well, the reason is I know that the absolute value of f of x minus L is equal to the absolute value of x. And ultimately, we want to prove that that value is large because we want to disprove that it's less than epsilon. So we want this absolute value of x thing to be really big and not really small. So if we're looking at x equals -1, the absolute value of x is going to increase as we go in the negative direction, but it's going to decrease if we go in the positive direction. So if I take -1 minus delta over 2, that's going to make the absolute value of x bigger so that we know it's going to be bigger than epsilon. That's our ultimate goal. So again, if we take the distance from x to c, that's going to be the distance from -1 minus delta over 2 to -1. And we do a little bit of algebra here. The negative ones are going to cancel out. We get the absolute value of negative delta over 2, and that becomes delta over 2, which is less than delta, just like we want. But on the other hand, if we look at the absolute value of f of x minus L, if we plug in x equals -1 minus delta over 2, we know this is just equal to the absolute value of x, and that's the absolute value of -1 minus delta over 2. Now our goal is to disprove the statement that this is less than epsilon. We actually haven't picked a value of epsilon yet. And the reason for that is I wanted to go through this whole reasoning to see what is the distance from f of x to L that we get. So this way, we can look at the distance here and say, okay, pick a value of epsilon that's smaller than this, so that this will always be bigger than epsilon. Well, this thing right here, the absolute value of -1 minus delta over 2. Because delta is positive, we can write this as 1 plus delta over 2. And this is always going to be greater than 1. So because we now know the distance from f of x to L is going to be greater than 1 for our choice of x, we can go back and choose the value of epsilon. So now we say, let epsilon equal 1. So we've chosen our value of epsilon equal to 1, and we've said, suppose we have any value of delta greater than 0. We can find this value of x right here, And this value satisfies the condition that the distance from this limit input -1 is between 0 and delta, because it's delta over 2. But on the other hand, the distance from f of x to L, where L is 0 here, that's always going to be bigger than 1. So it's never going to be less than epsilon. So we have a situation where this first condition is true. It's supposed to imply the second condition, but this statement is false. So this statement right here cannot be true for any value of delta, which means that that delta does not exist. So we've disproved the statement for epsilon equals 1, which means we've disproved the entire statement. So this limit right here does not equal 0. Now you might have noticed that if we look at these proofs where we're disproving that a limit equals some number, and we compare that to a normal epsilon delta proof where we prove that a limit does equal some number, it seems kind of backwards. Because normally, when we do an epsilon delta proof for a limit, we start by saying, let epsilon greater than 0. So we don't pick a value of epsilon, someone else gives a value of epsilon to us, and then we construct a delta. But in this case, when we're disproving a limit, we pick our own value of epsilon, and then we take delta greater than 0 to be any number. So it's kind of the opposite of what we would normally do in an epsilon delta proof. And the reason for that is, again, this first statement here, for all epsilon greater than 0. If we want to prove that this statement is true for all epsilon, then we have to accept any epsilon and prove that this statement always works. But if we want to disprove that this statement is true for all epsilon greater than 0, all we have to do is find one epsilon where it doesn't work, which means we get to choose the epsilon, and now our job is to show that there doesn't exist a delta, which means we have to prove this statement fails for any value of delta that we're given. So that's why there's kind of this reversal of which value we get to pick and which value we have to prove for every possible number. Now it's time to prove the final statement, which is that limits are always unique. In other words, if we have that the limit as x approaches c of f of x equals some value of L, but this same thing also equals some value m, then this implies that L equals m. So anytime a limit equals two numbers, those numbers are always equal, which means there's exactly one value for this limit if it exists. So in order to prove this, we're again going to use that epsilon delta definition of the limit. So let's suppose that the limit as x approaches c of f of x equals L, and it also equals m. Then this epsilon delta definition of the limit is going to be true when we put L in here, and it'll also be true when we put m in here. So we want to prove that L equals m. Now it turns out that proving L equals m directly is kind of difficult. But what we can do instead is show that the distance from L to m is really, really, really small. So small that it has to be 0. And here's how we're going to do that. Here's the value of f of x. Here's the value of L, and then down here is the value of m. Now, when we look at the epsilon delta definition of a limit, the thing that it gives us is the distance from f of x to L is less than epsilon. So this length right here is going to be small. We can make it less than epsilon. And if we do the same thing with the limit being equal to m, we can show the distance from f of x to m is also less than epsilon. We can make it really small. Now what we're interested in is proving that L equals m. So we want to show that this distance here, the distance from L to m, is small. But we can do that because if we know that this length here is less than epsilon, and this length here is less than epsilon, then the distance between these 2 points is going to be less than 2 epsilon. This is something called the triangle inequality, which basically says the shortest distance between 2 points is a straight line. So if we can get from L to m by going through f of x, and this length is less than 2 epsilon, then the length from L to m also has to be less than 2 epsilon. So let's take this picture right here and make it a little more formal. So let epsilon greater than 0. We can use the epsilon-delta definition right here because it says that some statement is true for all epsilon greater than 0. So because the limit as x approaches c of f of x equals L, we know there exists some value of delta. I'm going to call it delta L because it corresponds to the limit L here. So this is some value greater than 0 such that if the distance from x to c is less than delta, that implies that the distance from f of x to L is less than epsilon. Now we aren't just interested in L, we're also interested in m. But we can do this exact same delta-epsilon definition, except instead of L, we plug in m, and that's going to give us a different value of delta. So we also know that there exists a value of delta that corresponds to the limit m. So this delta doesn't have to be the same as the delta for the limit L. So I'm going to call it delta m to show that it might be different. So we know there's a delta m greater than 0, such that if the distance from x to c is less than delta m, then that implies that the distance from f of x to m is less than epsilon. Now this is the part where we use the triangle inequality. In order to do that, we first have to actually find a value of x so that the distance from x to c is less than delta L, and it's also less than delta m, because we want to use both of these statements at the same time. So this value of x has to satisfy this condition, and it also has to satisfy this condition. So in order to do that, we have to be a little bit creative about how we pick the value of x. And the way to do it is we take x is equal to c plus the minimum of delta L and delta m, and then divided by 2. Now, remember when we were looking at the earlier examples, the value that we would take would be the value of c, this limit input, and then plus delta over 2. Or in the second case, we took -1 minus delta over 2. But when we did that, we always took the value of delta and then we divided it by 2, so that the distance from this to c is delta over 2, and that's less than delta. In this case, we want the distance to be less than delta L and also less than delta m. But that's the same thing as the distance being less than the minimum of delta L and delta m. So here I just took c plus that minimum over 2 to make sure that it's less than both. So we have a value of x here, where the distance from x to c is greater than 0, and it's less than both delta L and delta m. So this implies the distance from f of x to L is less than epsilon, and the distance from f of x to m is less than epsilon. We don't really care about either of those. What we care about is the distance from L to m. And this is the part where we use this triangle that I drew right here. Because when we apply the triangle inequality, what it tells us is the distance from L to m is less than or equal to the distance that we get by going from L to f of x and then f of x to m. So this is less than or equal to the distance from f of x to L plus the distance from f of x to m. And so this f of x minus L, this is less than epsilon. This one is also less than epsilon, so in total this is less than 2 epsilon. Now let's recap what we did here. We started by saying let epsilon greater than 0. We did a bunch of math in the middle. We don't really have to worry about that right now. What matters is we started with epsilon greater than 0, and we proved that the distance from L to m is less than 2 epsilon. So for every positive number epsilon, the distance from L minus m is less than 2 epsilon. But the only way that that's true for every single positive number, the only way that the distance from L to m is less than every positive number, is if the distance from L to m is 0. So we therefore get that the distance from L to m is equal to 0. And of course, that's only possible if L equals m. So we started out by assuming that this limit of f of x equals L and it equals m, and we've said therefore L equals m. So we now know that limits are unique, and that is the power of the epsilon delta definition of the limit.